Visit us at Eduvvo. Thank you for calling Eduvvo.
In this course, we'll review multifaceted ways of developing secure software. I'll start by going over what we mean by software security, then show you various software security threats. We'll also see how to design secure software. In addition, I'll be covering secure coding best practices as well as how to test your software for security. Now, let's get software security is a broad term encompassing many topics, and I'll help you gradually develop your understanding of software security throughout this course. In information system security, vulnerability refers to weaknesses exploited by attackers to breach confidentiality, integrity, and availability. Vulnerabilities in software arise mainly due to design flaws or coding errors, also called bugs. Therefore, software security is an attempt to minimize the introduction of design flaws and bugs during a software development lifecycle, or SDLC. Software security is primarily about preventing artificial security threats instead of those naturally occurring. Almost every aspect of our lives today are touched by software. Therefore, software security breaches could have a big impact on our lives. An important part of our job as a software security professional is to raise awareness so that the management invests resources in software security and software developers use the best practices in software security. The most effective way of raising awareness in software security could be talking about in terms of its probability and consequences. As we all know, the probability of software security breaches is increasing these days. You can check this out yourself by visiting the Common Vulnerabilities and Exposures, or CVE, website. The CVE website is a repository of all the reported software vulnerabilities. After going through the CVE list, your management team and software developers will definitely say that the software security threats are real and everywhere. The consequences of software security breaches are grave. For example, there is industry-enforced fine called Payment Card Industry Data Security Standard, or PCI DSS, violators end up paying hefty fines, often in the range of millions of dollars. There are also reporting responsibilities managed by the government. Most of the U.S. states make it mandatory to notify the victims once a security breach occurs. With all the resources you've been exposed here, you should now feel confident when explaining the importance of software security. A critical part of preparing yourself as a competent software security professional is to learn the terms used in the field. Threats are anything capable of doing harm to your software system. Vulnerabilities are any weaknesses exploitable by the threats. Controlling the threats is almost impossible, while managing vulnerabilities is much more feasible. This is why many organizations today focus on vulnerability management. The most comprehensive software security term is defect. Defects refer to any errors introducing software security vulnerabilities. Flaws are design errors causing software security vulnerabilities. Bugs are coding errors leading to software security vulnerabilities. When you're making an important decision through a conversation, the use of precise terms can make a huge difference. Acknowledging the fact that there is no perfect software security is the first step in mastering software security. The most practical way to handle software security is to manage software security as you have to do when dealing with chronic illness. This is why risk management plays a crucial role in coping with the challenges of software security. Probability and consequences are how risk manifests itself. Probability indicates how possible for a software vulnerability to be exploited by a threat. Consequences measure the extent to which a software security incident can be damaging. For example, we can ask this question: what is the risk of a denial of service attack compared to a phishing attack? To answer this question, the first thing to think about is how probable the denial of service and phishing attacks are. The second thing to consider is the consequences of the denial of service and phishing attacks. Therefore, managing software security is the process of managing risks associated with software to minimize both probability and consequences. There are a number of useful software security resources you can tap into. The first one I'd like to share is the Build Security In website. This website is sponsored by the Department of Homeland Security, or DHS. You can find a number of freely available software security resources, such as best practices, guidelines, and tools. In particular, on the Build Security In website, you can find a software assurance pocket guide series. Depending on your software security interest, you can pick and choose your pocketbook in PDF and study it. Another very well-known software security online resource is the Open Web Application Security Project, or OWASP. OWASP is a nonprofit open source project. One of their most famous works is the OWASP Top 10 list, which lists the top 10 web application software risks. IEEE Security and Privacy is an academic journal specializing in security. They have been publishing articles focusing on software security, and many of them are available at one of the Build Security In sites. What I showed so far is only a fraction of what's available online. You certainly don't have any lack of information, but you definitely need some guidance, which I'll provide throughout this course. There are various threats to software security, including the ones originating from computer hardware. Eavesdropping devices can be installed to bypass software security countermeasures. For example, hardware keyloggers can be used instead of software keyloggers. Man-made disruptions to hardware, such as power outage and sabotage, can cause software to fail and malfunction, therefore affecting software security. Natural disasters can destroy computer hardware on which software is running. These natural disasters include earthquakes, volcanic eruptions, tsunami, etc. We need to realize that software security relies on hardware security or physical security. As a result, software security needs to include countermeasures against hardware security failures. Some of these countermeasures include considerations for geographically dispersed redundancy to avoid a single point of failure, as in cloud computing, uninterruptible power supply, or UPS. Finally, physical security to prevent the theft of or damage to computer hardware. Software relies on hardware, so don't forget about computer hardware when considering software security. An obvious threat to software security is the one at the code level. These code level threats could be either unintentional or intentional. There are many ways software developers can make coding mistakes, mainly due to the lack of secure coding knowledge. For example, there are built-in function calls in C you can make, which is vulnerable to buffer overflow attacks. Intentional code level threats include malicious insiders who can plant a logic bomb in the source code. The logic bomb will eventually make the software misbehave or vulnerable. To prevent unintentional code level threats, software security education and training is critical. Also, automation such as static and dynamic code analysis to identify vulnerabilities is the key. Once identified, the vulnerabilities need to be managed properly until they are mitigated satisfactorily. To prevent intentional code-level threats, security oversight, such as peer code review, job rotation, and mandatory vacation, is essential. Code-level threats are preventable, but requires a lot of resources to manage them properly. It is often the case that organizations solely focus on secure coding to improve software security. However, secure design is more fundamental and could have an even bigger impact on software security. Software developers often face recurring security problems. For example, improper info validations make software vulnerable to attacks such as SQL injection attempts. There are usually well-known solutions to these recurring security problems an individual developer can quickly adopt. These well-known solutions are referred to as design patterns for security. At this point, developers have three choices. The first is not doing anything about the vulnerability, which is the worst. The second one is ignoring the existing best practices in the form of design patterns and develop your own, which could be suboptimal. The last one is using the design patterns. Remember that design patterns provide a local solution and can only partially address the security problems at hand for that individual developer unless it is enforced consistently throughout the software development process. Therefore, the rest of the software could still be left with improper input validation in this case and vulnerable. This is why a local security countermeasure, especially in the form of a design pattern, is insufficient for a global problem such as security. Not using design patterns for recurring security problems is definitely a threat to software security. However, the local use of the design patterns still leaves the software vulnerable. Software as a whole should be secure to ensure software security. Any security hole, even if there is only one, can lead to the security breach of the entire software. Because security is a problem requiring global treatment, software needs an overarching design decision to address security problems. These overarching design decisions are called architectural design decisions. Therefore, we need architectural design decisions to improve software security. As in design patterns, there are also recurring architectural design challenges. Widely accepted solutions to these recurring architectural design problems are referred to as architectural patterns. These architectural patterns provide solutions to the quality attribute problems of software, such as security. For example, single access point is an architectural pattern. The core idea behind this pattern is to make only one access point available to a software application. This way, all you have to check to control access to the software is the single access point you designate as a designer. Also note that the architectural design patterns are not perfect and has its own trade-offs. For instance, the single access point could also become a single point of failure. The absence of architectural decision-making for security is typically a good indicator for potential security vulnerabilities. Collecting security requirements is a challenging task. You need expertise in requirements engineering as well as information system security, which is often a rare combination. The biggest problem is that customers and users also don't know what they want with respect to security. On the other hand, requirements engineers don't know what questions to ask to elicit security requirements. This combined lack of security expertise lead to missing or unidentified security requirements. These unaddressed security requirements, in turn, result in security vulnerabilities. There could be a few solutions to mitigate the requirements level threats to software security. The most obvious solution is to provide an extra resource to the team of requirements engineers. That is, provide a software security expert to work with the requirements engineers. This is easier said than done because of the monetary investment required. A compromise could be the use of a comprehensive security requirements checklist. Each stakeholder during the requirements process can work with the checklist. Then the requirements engineers can ask intelligent questions while the customers or users can provide educated answers. Correcting the missing security requirements tends to be costly, as in the case of any missing requirements. You might have to rewrite the entire software in the worst-case scenario. Threat modeling is a must for secure software engineering. Let's define threat first. A software security threat is anything or anybody that could do harm to your software system. Threat modeling starts with identifying threats to your software system. We then analyze the identified threats. Categorization of the threats comes next. This categorization process is particularly important because it provides a basis for prioritizing the threats. Finally, you are ready to mitigate the threats. Threat modeling takes the design specifications of your software as an input and produces mitigation strategies as its outputs. One of the well-accepted threat modeling approach is called STRIDE. STRIDE stands for spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. STRIDE, in this case, serves as a starting point to reason about threats. This is very similar to the use of tactics when conducting an architectural analysis for security. The threat environment is constantly changing, which is why threat modeling should be ongoing throughout the lifetime of a software system. Design is an essential element of software engineering. Implementing without a solid design is like jumping out of an airplane without a parachute. Coding is expensive. Once you start writing the code and discover a major mistake midstream or towards the end, it is most likely that you will have to start over. To avoid this very expensive trial and error process, good software engineering mandates design which allows software developers to try various coding possibilities without actually writing the code. There are a number of design techniques widely used in the software engineering industry, including modeling languages dedicated to the design process, such as Unified Modeling Language or UML. In solving software security problems, the design process and its artifacts are even more important since they capture the security design decisions. The absence of design documents most probably implies that nobody thought about how to secure their software. Even if informal, undocumented design decisions do exist, they are not too much help because the security design decisions cannot be tracked effectively, and therefore their enforcement will be almost impossible. This is why formal security design process and its documentation is so critical. We know secure design is important, but how do we go about secure design in reality? Security tactics are a useful tool that can help you immediately start reasoning about secure software design. A security tactic is a design concept that addresses a security problem at the architectural design level. There are four main categories of security tactics. The first class of tactics help detect attacks. The second type of tactics are used to resist attacks. The third category of tactics react to attacks. There are also tactics that help recover from attacks. There are mainly two possibilities of using tactics. One is using them during the requirements gathering process, and the other is using them for the design process. Both of these possibilities use the tactics as a checklist. When using tactics for design process, you need to be asking the questions like, have I made any design decision on authenticating actors? The nice thing about tactics is that they're easy to understand and can be very easily picked up very quickly. No extensive training is necessary before its use. Security patterns are well-known, secure design solutions to recurring software security problems. There are two types of security patterns. The first type is design patterns for security, providing software security countermeasures at the detailed design level. The second type is architectural patterns for security, offering secure software architectures. When applied consistently throughout the entire software system, a design pattern becomes an architectural pattern. For example, an input validation design solution, such as intercepting validator, is a design pattern when used individually by only a small subset of developers without an overarching strategy or vision of how it will be implemented across the entire software project. This ad hoc adoption of design patterns for security without an architectural vision or philosophy is dangerous, especially because the effectiveness of the individual implementation cannot be verified objectively and timely. In addition, duplicate implementation efforts by developers not communicating with each other about the use of a design pattern could lead to the inefficient use of software development resources, while the standard implementation of the design pattern could be used throughout the software system consistently and coherently. Therefore, the most effective way of using security patterns is to use them architecturally with the constant supervision of the software architect who has the global view of the software system. Security vulnerabilities need to be managed systematically to help identify weaknesses in the affected source code of a software system. A close inspection of the source code sometimes leads to something more fundamental, that is, a design flaw. Many automated vulnerability management systems take advantage of the Common Vulnerabilities and Exposures, or CVE, database maintained by MITRE. CVE is a repository of all the reported security vulnerabilities associated with a specific software system. Each CVE entry has a unique identifier, which is commonly used by many commercial vulnerability management systems to refer to a specific software vulnerability. On the other hand, Common Weakness Enumeration, or CWE, categorizes the vulnerabilities identified in CVE. Therefore, CWE has much fewer entries in its database and offers a list of all the different types of vulnerabilities instead of their instances. CVE has too many software product-specific details to be useful for us to use it as a basis of reasoning about possible software vulnerabilities in general. To the contrary, CWE can provide more useful insights on what can go wrong with software security. More importantly, some of the CWE categories could be tied back to design flaws, which may be addressable by the use of a security pattern. Therefore, CWE entries are a useful resource available to software security practitioners. They can think of some of them as symptoms of missing or inadequate design decisions made on software security. An architectural analysis for security is a software engineering process used to discover the absence or presence of design decisions on software security. AAFS or OFS consists of 3 phases. The first phase is Tactic-Oriented Architectural Analysis, or TOAA, also pronounced as TOA. The second phase is Pattern-Oriented Architectural Analysis, or POAA, pronounced as POA. Finally, the third phase is Vulnerability-Oriented Architectural Analysis, or VOAA, pronounced as VOA. During the TOA phase, you can use security tactics as your checklist to inquire about whether any architectural design decisions have been made to address the security tactics. During the POA phase, security patterns are your checklist to verify if a particular security tactic has been refined into a more specific design decision. If a person, ideally a software architect you are interviewing, can say that they considered a tactic but cannot elaborate on how that tactic got instantiated into a concrete pattern, there is definitely something wrong. Most probably, this means that the tactic just remained as a tactic, but never got further developed into a more specific design decision in the form of a security pattern. The VOA phase is where you examine the source code and look for any evidence of properly implementing security design decisions into countermeasures that address related vulnerabilities. Using all these three phases of ops, it is possible to conduct a thorough inspection of software with respect to its security practices. OpenEMR is an open source project that implements an electronic medical record system, or EMR. This project released its first version of software in 2001. OpenEMR software has a pretty significant code base containing more than 500,000 lines of code. It also has a relatively big user base. We'll be using OpenEMR as our case study to learn together how to conduct a typical architectural analysis for security. To apply the tactic-oriented architectural analysis phase of ops to OpenEMR, it is important to have access to a person who is deeply knowledgeable about the software. Most probably, this person is one of the software architects of OpenEMR. You will be interviewing the software architect while using the security tactics as your checklist as shown in the table here. One of such interview questions could be on the security tactic of verifying message integrity. Does the software do anything about the verification of message integrity? The answer may be mixed. In the case of OpenEMR, the architect said that message integrity verification is partially supported by means of standardized library function calls specializing in user input sanitization. Next, you need to think about what this answer truly means in terms of security design rationale and assumptions. The POA phase is an aid that helps with this further reasoning in more detail. As demonstrated in our OpenEMR case study, during the TOA phase, your goal is to find out whether there was any thought of doing anything about a specific security tactic being questioned. If they did think about it, the next step is to discover whether they made a design decision to adopt the security tactic or not. Pattern-oriented architectural analysis, or POA, leverages security patterns as a checklist to see if a more concrete design decision in the form of a security pattern has been made to further develop the idea of a tactic. The core question here is whether they are following up on the design decision made during the tactic-oriented architectural analysis stage. If they did, is the idea a step closer to a piece of code which software developers can better relate to? The true evidence of this refinement is the official, system-wide adoption of a security pattern. If they didn't, this implies that there is absolutely no design idea implementation in the code. Let's assume that in the case of OpenEMR, we decided to pursue the verify message integrity tactic in the TOA phase, or tactic-oriented architectural analysis phase. A security pattern that further refines the verify message integrity tactic is intercepting validator, as shown in the UML diagram here. Note that the security pattern actually shows in detail how to verify message integrity by the use of design elements such as various validators interacting with the client and the target. The gist of the design idea here is to verify all the client inputs using validators before they are used by the target. A validator implements rules specific to a certain type of client inputs. As a result, full, partial, or no client input will eventually be forwarded to the target. If you can see this tangible transition from a tactic to a pattern in the process of security design decision-making, you are now more confident about the possibility of something being actually done in the code to address the message integrity verification problem. Therefore, the POA phase, or pattern-oriented architecture analysis phase should focus on finding the evidence of the adoption of a relevant security pattern whose origin can be traced back to a tactic selected during the TOA phase, or tactic-oriented architecture analysis phase. After the pattern-oriented architecture analysis, you are now ready to examine the source code. The first thing to do during the vulnerability-oriented architecture analysis phase is to locate the OpenEMR source code implementing the security pattern identified during the pattern-oriented architectural analysis phase. In our case study, the security pattern is intercepting validator. The next step is to check if various parts of the OpenEMR source code takes advantage of the intercepting validator. To do this, we need to rely on the vulnerabilities resulting from the misuse or no use of the intercepting validator pattern. There is a very common vulnerability caused by the misuse or no use of the intercepting validator pattern. SQL injection vulnerability is one of them. Armed with this information, we can now check the areas of the OpenEMR source code where SQL injection is possible and see if the developers are actually using or misusing the intercepting validator code if the intercepting validator code does exist. It is always possible that only a few developers are properly using the intercepting validator code, leaving the system still vulnerable to SQL injection attacks due to its parts where the intercepting validator code is not used or misused but should be used properly. In the case of OpenEMR, it turns out that there is no implementation of the intercepting validator pattern at all, not to mention the full and appropriate adoption of it. Software security anti-patterns capture the undesirable security practices that make the software more vulnerable to attacks. Security anti-patterns are wider in their scope than security patterns because there are many more ways to do harm than to do good. Here are some examples of what not to do when trying to develop secure software. We often see websites allowing files to be uploaded without specifying the list of allowed file types. Open-ended approach, not specifying exactly what file types are allowed, or blacklisting, is an anti-pattern because it violates the secure design principle of fail-safe defaults. In this scenario, the web application takes a URL as an input and automatically redirects users to the URL without validating the URL. This URL could be a phishing site or can contain malicious code. Unrestricted path traversal is another common but critical programming mistake. In this case, users can have access to the directories other than those originally intended for proper use. Proper and fine-grained access control is necessary to restrict the access to the directories not intended for traversal. If the restriction is not imposed, you may end up exposing your entire file system. Remember the least privilege design principle here. This one is a no-brainer. You don't want to embed your critical password to your code in plain text. I hope that you now understand what anti-patterns are and will start thinking about security patterns that could mitigate these anti-pattern threats. Note that we have an opportunity here to do really creative architectural design to deal with many small but significant mistakes made by software developers. Secure coding means not making programming decisions that make the software vulnerable to attacks. Some of these undesirable programming decisions are well documented in the form of CVE or OWASP top 10 entries. Therefore, secure coding practices should avoid these unsecure ways of programming and replace them with their secure version. Sometimes this is as easy as making a safe function call instead of its unsafe counterpart. Other times, secure coding alone is not enough, and higher-level decision-making is necessary, which is more architectural and design-oriented in nature. Despite its limitations, software developers should realize that secure coding practices are low-hanging fruit. The return on investment in this area is immediate and high. This is why every developer needs to be exposed to at least the most fundamental set of secure coding best practices. Software applications vulnerable to buffer overflow attacks are classic examples of the results of insecure programming decisions. Buffer overflow attacks exploit the lack of user input validation. The question here is how much freedom you can give in terms of what users can provide to the software. The answer should be as little as possible to get the work done. You should be using the least privilege principle here. There are different containers in your main memory, one of which includes an area storing user inputs called buffer. Stack and heap are examples of other containers in the main memory. When an attacker puts too much information into the buffer, it can overflow into other adjacent containers in the primary memory of your computer. This can contaminate the information already stored in these other containers, therefore making the software misbehave. Buffer overflow attacks can crash your program or an entire operating system. A more sophisticated buffer overflow attack can execute a malicious piece of code written or simply used by the attacker, which can in turn be used to take over an entire operating system. Buffer overflow vulnerabilities are relatively easy to detect and fix. Therefore, secure coding practices as well as the smart use of code scanning tools can prevent most of the buffer overflow attacks with relative ease. Buffer overflow attacks are common, and therefore there exist relatively well-developed countermeasures against them. The first option is to use a programming language that supports automatic bounds checking of buffers. These languages include Java and Python. A better solution is architectural and to use a built-in language-specific library module that implements input validation in the form of safe buffer handling. To check if there are any missed opportunities for properly managing the buffers, it is recommended to use a code scanning tool to detect the presence of any buffer overflow vulnerabilities. Compilers can also alert the programmers when an unsafe function call is made. A more advanced compilers can compile a program so that protection against buffer overflow attacks can automatically be compiled in with the program. Finally, your operating system can also be written to make buffer overflow attacks more difficult to launch. For example, the operating system can enforce more stringent memory access control so that buffer overflows cannot infringe into the protected areas of the main memory. Although there are many ways of preventing buffer overflow attacks, the secure coding practice at the software developer level is the most surefire way of stopping buffer overflow attacks. Authentication is one of the most common forms of access control. Session management complements authentication by making the effect of authentication expire over time. Authentication verifies the identity of a supplicant who provides security credentials such as passwords. Authentication and session management often break due to reasons such as password cracking, insecure communication channels, insider threats, or social engineering. More importantly, software developers often use their own custom code to implement authentication and session management. Building your own custom authentication and session management scheme is hard and prone to error, eventually leading to security vulnerabilities. Once compromised, broken authentication can allow unrestricted access to the software system resources, which is extremely dangerous. There are a number of well-established authentication and session management solutions available to you as a software developer in the form of software security frameworks. There is no need to write your own custom code from scratch. Software frameworks provide generic but necessary features such as security through an easy-to-use abstraction. That is, frameworks users can simply utilize the interfaces of the frameworks to take advantage of its professional software implementation of the needed feature. Frameworks also allow its users to easily extend its existing capabilities to better satisfy special requirements in a particular domain. When choosing security frameworks for your own project, keep in mind that they meet a certain standard, such as OWASP's Application Security Verification Standard, or ASVS v2 and v3. ASVS v2 addresses authentication, while v3 focuses on session management. Some additional criteria to use when searching for the best framework for your authentication and session management needs are its reputation and acceptance in the developer community, reports on the known security vulnerabilities of the framework itself, and support available to answer your technical questions and to maintain the code base. This technical support is particularly important because the threat environment for the security framework is constantly evolving. The framework should be kept current to effectively deal with the newly emerging threats. Most of security frameworks implement authentication and session management. Therefore, you should have a lot of choices. A direct object reference can happen when a software developer exposes a link to system resources such as a file or directory. Without proper access control, it is possible for an unauthorized user to have access to unintended resources. For example, this type of programming oversight commonly occurs in web applications. Let's say that Mallory is expected to only access her own credit report, but simply replaces her ID parameter value of the URL with Bob's. Now she has access to Bob's credit report. The coding mistake in this scenario is that without proper access control, the programmer exposed a direct reference in the form of ID parameter to system resources, that is, credit reports. What is at risk here is the data or information that could be sensitive and should be protected. The bottom line here is that uncontrolled direct access to system resources is bound to result in data or information leakage. Therefore, software developers should do their best to disallow this type of insecure direct object reference. The best way to minimize the possibility of introducing the direct object reference vulnerability is to test your source code. Luckily, spotting this type of vulnerability is relatively easy. A routine code review should be able to detect most of this type of vulnerabilities. When doing the code review, you need to pay attention to all object references and check if the reference mechanisms go through a proper access control step, restricting the access only to authorized users. Automated tools may have a difficult time in detecting direct object reference vulnerabilities, mainly because its inability to tell what is allowed and what is not. Therefore, manual inspection is a must in this case. Programmers often forget to guard their sensitive information. So what is considered sensitive? Personally identifiable information, or PII, is one of them. PII includes information such as names, social security numbers, biometric records, and so on. Other sensitive information includes credit card numbers, tax IDs, usernames, passwords, etc. These are primary targets of attackers because they could use this information to commit crimes such as identity thefts and financial frauds. Access control plays an important role here. Only authorized users should have access to sensitive data. Encryption is another critical technology to protect the data both at rest and in transit. Not providing adequate protection, such as proper access control, and encryption is the most common programming mistake software developers make in this scenario. The most basic and fundamental countermeasures against sensitive information exposure are access control and encryption. There are primarily three aspects of access control which software developers should be aware of. Identification is usually the first step in access control and retrieves information on who the supplicant claims to be. Authentication then tries to verify the claimed identity by using credentials such as passwords and biometrics data. Authorization is the step where the supplicant receives its permissions to have access to protected resources. The permissions need to be carefully controlled according to the need to know of the supplicant. When considering encryption for protecting your information, you need to take many factors into account, such as strength of encryption algorithms, configuration of encryption scheme of your choice, like key length, different scenarios in which attackers can bypass the protection provided by the encryption. For example, man-in-the-middle attack is always possible if the encryption process is not done properly. Here, software security frameworks can also help the developers avoid implementing their own access control and encryption solutions. Most of the security frameworks provide well-tested, sophisticated access control code ready to be used. There are quite a few more easy-to-make coding mistakes that are well-publicized but still occurring every day. As in buffer overflow attack scenarios, info validation can make a big difference in preventing other common attacks such as SQL injection and cross-site scripting. SQL injection typically appends a piece of SQL code to an expected user input so that the unexpected SQL code portion of the user input is executed by the database engine to produce the outcome desired by the attackers. These outcomes could be bypassing authentication or retrieving additional data. Cross-site scripting also embeds malicious code into the user input so that the code gets executed in another website that was not originally intended to be used by the attacker. Remember that a more fundamental solution is necessary to address many of these attacks exploiting info validation vulnerabilities. The key here is an architectural solution that is overarching and lasting. An example of this kind of solution to input validation vulnerabilities is intercepting validator security pattern. Proper configuration is easier said than done. A software product with all the security bells and whistles could still be vulnerable if it is misconfigured in the production environment. Error handling can reveal sensitive information on the inner workings of the software, therefore providing the attacker with the information needed to defeat the existing security countermeasures. It is the best to catch as many errors as possible in your program and filter the error information so that the users have access to only the information they need to do their job. Although I advocate the reuse of source code in the form of software security frameworks, it is necessary to verify the trustworthiness of the third-party software components before making a decision on their adoption. Testing for security is essential to ensure software security. There are essentially three different types of general testing techniques which can still be used for testing software security. Black box testing is one of them, and its name implies that the testers don't have access to the source code. White box testing is the opposite of black box testing. It does have full access to the source code and designs its tests based on the knowledge of the source code. Gray box testing is the hybrid of the black box and white box testing. There is also more security-specific way of categorizing software testing. These testing techniques are static analysis, dynamic analysis, and penetration testing. Software security has traditionally focused on testing a lot, which is why security testing is a field that is very mature and offers very good tool support. Static analysis refers to the analysis of source code. It examines the text of a program. Therefore, the security testing can be done without executing the source code, which is why it's called static. This also means that you don't need a program that is fully functional to do your testing. Software bugs are usually found in hard-to-reach states or unusual circumstances. They are also language-specific. For example, memory management is done manually in languages such as C, while it is automated in Java. Static analysis has some significant limitations too. For example, only a fixed set of bugs can be detectable due to its reliance on signatures. If there is no signature for a bug, it is not detectable as in antivirus software. Static analysis also produces lots of false positives, which requires manual inspection to determine if what is detected is truly a bug. Last but not least limitation is its inability to detect design flaws. There are a number of static analysis tools for software security. One thing to remember is that static analysis is not perfect. There could also be many false negatives, which is particularly dangerous since it gives you a false sense of security. There are quite a few static analysis tools available for software security practitioners. These tools know what security vulnerabilities look like. Although manual code inspection is always possible through peer code reviews, it is error-prone and not scalable. The manual approach is also not as comprehensive and complete as its automated counterpart. The use of software tools is also much cheaper than hiring a human expert to do the same amount of work. This relatively inexpensive nature of the static code analysis tools also allows more frequent testing. There are a wide range of approaches used by static code analysis tools. It can be as simple as a search tool capable of interpreting regular expressions. An intermediate approach could be a more customized tool that can do a lexical analysis based on predefined vulnerability patterns. However, this approach does not consider a context in which a pattern is detected. The most advanced approach is using abstract syntax trees borrowed from compilers, which can consider semantics and has more flexibility in its scanning scope. For example, the scanning can be done at the function, module, and global levels. Static code analysis programs are essential in the toolkit of a software security professional. Unlike static code analysis, dynamic code analysis tests software while it's running. Dynamic analysis can be done in two ways. One is black box testing, and the other is white box testing. In the case of white box testing, it tests the software both in its intended and unintended ways of use. It validates the security functionality of the software and checks whether implementation conforms to its original design. There are some requirements to be met to conduct effective white box testing. The obvious requirement is access to source code. The testing team also needs the knowledge of what makes the software secure and vulnerable. In addition, they need to think like an attacker. The best time to conduct white box testing is during the unit test phase, although it can be done anytime during a typical software engineering lifecycle. Unlike the white box testing, black box testing can only depend on the software requirements or specifications. Testers don't have the knowledge of the inner workings of the software. Therefore, they have to be more creative in coming up with various ways of testing the software for security. Dynamic code analysis has its own merits over static code analysis. One of such advantages is that it does not require source code. Let's take a look at some examples of dynamic code analysis tools. The first one is IBM AppScan. Although it has its static version, IBM AppScan can conduct a dynamic code analysis too. It is a commercial product and therefore quite expensive. You can visit their website and download a trial version as you can see here. With this trial version, you can only scan a demo website designated by IBM. However, the experience is enough for you to get a feel for how the tool works. There are also open source dynamic analysis tools available. Nikto is one of such tools and specializes in scanning web applications. A new trend in dynamic code analysis is its migration to the cloud. New cloud-based dynamic code analysis services are popping up every day, and one of such services is Qualys, as shown here. In addition to the dynamic code analysis tools I'm introducing here, there are many more available out there. Penetration testing is also called ethical hacking. It is a professional way of testing the security readiness of a software system by launching attacks similar to those used by malicious attackers. Penetration testing stress tests the software system in the wild and in its own habitat instead of simply identifying its vulnerabilities in an isolated environment. Therefore, it's more realistic. Penetration testing is most effective when done in a white box mode. Some aspects of penetration testing can be conducted by using automated tools. However, a thorough penetration test goes beyond the automated testing and continues until the human testers exhaust all the possible testing techniques. An ideal attitude of a penetration tester is believing that the automated testing simply provides leads which should be further pursued during the manual testing phase. Ultimately, a human judgment call is necessary anyway to decide whether a vulnerability is a false positive or not. The biggest difference between criminal hacking and penetration testing is that one is done without the permission of the owner of the software system, while the other always requires a formal authorization before the testing begins. One of the most famous penetration testing suite is Kali. It comes with numerous ethical hacking tools and provides a very comprehensive software toolkit for a penetration tester. Kali's predecessor is Backtrack, and the Backtrack Linux distribution is no longer being maintained. Vulnerability management is becoming highly important due to the exponential growth of the number of software and their versions to be maintained in an organization. Each software comes with a burden of various vulnerabilities that need to be addressed individually. Systematic tracking is critical to be able to minimize the impact of an obscure vulnerability to be exploited and leading to becoming a major security incident. Effective vulnerability management follows a process. The very first step of a typical vulnerability management process is to develop vulnerability management policies. Next is to discover the actual vulnerabilities. The discovered vulnerabilities then need to be analyzed and prioritized according to their risks. The higher priority vulnerabilities are mediated first, and some vulnerabilities are simply documented and not mediated due to their relatively low risks. This process continues as long as there are known vulnerabilities. vulnerability management is getting more standardized by the introduction of vulnerability repositories such as CVE and CWE. Most of the commercial vulnerability management tools these days take advantage of unique CVE numbers associated with the specific vulnerability of a particular software program. For it to be effective, vulnerability management needs to be automated as much as possible. One of the most widely adopted commercial vulnerability management tool is Nessus. It is also branded as Vulnerability Assessment Tool. You can download the home version of Nessus for free and try it. As you already know, discovering vulnerabilities is simply one aspect of vulnerability management. Therefore, you need to check out the tracking and prioritization aspect of Nessus to fully appreciate the power of the tool. Thanks for watching this course. I hope you enjoyed it as much as I enjoyed creating it.